Alright, hello and welcome back. Let us get started with lecture number 2. So thanks for getting through the first one with me. We stopped right here on this first in-class exercise, and now it's time for another, just to get our minds warm again. So let me fix the definitions of 3 propositions. Remember, the proposition is just something that can be true or false. It's a statement. So I'm saying that P is false, Q is true, and R is true. What is this fancy operation altogether? So mostly I'm asking you to remember the symbols. Okay, so maybe take a second, try it yourself, and let us do it together. All right, so this is saying, okay, P is false. What does the symbol mean? It means or. Remember the vortex. P or Q, which is true, and my cat is scratching my chair. He has stopped. False or Q, which is true. And this is and not R, so not true. Okay? So let's work on it this way. Not true, that's pretty easy. That becomes false because negation takes true and makes false out of it. And now we're back. And now I'm back because my cat decided to walk away with my reading glasses. Okay, so not true is false. That's not too bad. And then we have the rest of it. And actually, let me put this down here. So this is now, okay, equivalent to false or true and false. Okay, now we can look at the table for and, because we got to do that one first with our parentheses. Well, true and false, well, they're not both true, so it's going to be false. Okay, so we have false or false. No use there. Or would give us true if at least one of them was true, but none of them are, so we have false in the end. Okay, so hopefully that made some sense. And we are now through our next in-class exercise, which I am calling Crushed Ice. Okay, so you might be wondering, how in the world do you go about writing your own truth table when you have a very big, long thing? Like, you got more than just this. You have all the stuff on the previous slide, for example. So the idea is you first put all of your variables, P, Q, and R, for example. Like, we'll do this one maybe. And then you put your work as you're doing it. So usually you save the final column for the final operation you're trying to show. So eventually we need to get to P or Q and not R. Okay? This is going to be hard. P or Q and not R. There. And then in between you put all the intermediate stuff. And then you fill out this table. Okay? And the intermediate stuff was, okay, what's not R if we have R? And then what's Q and not R? Because then we can just OR with a P, which we already have a column for. So you start with your variables, and then you do your intermediate stuff, and then you have your final thing that you're trying to show. So that's how you normally write a truth table. And the columns, they actually have a special order. They're defined by what these propositions are, right? P, Q, and R, because those are the variables. So we don't know what these are, so we need to try all the possibilities for P, Q, and R. And the rest of these follow from that. And so what you do is well, I shouldn't say right next to the final column, the final variable column goes true, false, true, false, true, false, dot, dot, dot. So it just keeps on alternating. True, false, true, false. And we're going to end up doing this 8 times because there are 2 to the 3 possibilities for P, Q, and R. Okay, so that's R. And then the one to the left of that goes 2 trues, 2 falses. It swaps half as often. And then the column to the left of that goes even slower. So now we're going to wait every 4 to swap between true and false. And eventually we're going to exhaust all our possibilities. So that's the order, and we're technically secretly counting in binary from the bottom up, or from the top down, depending on how you think about it. So there's always going to be, when you start with, like, you set c equals to 0 here, I'm calling it c for no good reason. Like, c is equal to 0 here, and I start alternating every 2 to the c rows, so every 1 row. C equals 1 here. I start alternating every 2 to the 1 rows. Things like that. Okay, so we're really counting in binary, and now we can fill out the rest of this. Alright, here we go. So we just negate all of r, so r in this case is true, so I'm going to make it false. R in this case is false, so I'm going to make it true. And we can just play this game. False, true, and then we do q and not r. Now I have not r and q, and I can combine them. So, true and false, false, true and trues, true, false and false, false, false and true, false, there's a false, there's no false, false, false. And then we're ORing this with p, so this and p we're ORing together. So if there's a true somewhere, and there is in the first 4 cases, I don't even have to look at this one. I know I immediately get true. And then for the rest of these, it's going to be whatever this is, because if it's true, we finally make it true because of the OR, but if it's false, we're kind of stuck. And so for this example, we had false, true, true, which was this line. And we correctly discovered false. But this is how you write a truth table with all the possibilities. Okay? So let's do something easier. Take a second to write the truth table for p and not q. Okay? I can't wait to get back to the classroom, because then I can have you guys do this yourselves, and I can walk around, see how cool it was. So we start with all the propositional variables, p and q, and the ordering is very important. First goes those, and then p and not q. Well, actually, we can have one intermediate one, because why not? We can have not q, but if you're fancy, you can just go straight to the answer, if you'd like. P and not q. Okay, so that's all we need to make them all together. So what's the order again? It goes true, false, true, false, true, true, false, false. There's 2 to the 2 possibilities. And then this is not q, so we're just going to flip the q column. False, true, false, true. Hopefully this is becoming methodical now. P and not q. So we're considering these 2 columns, looking at each of these, and ANDing them together. So the only time it's ever going to be true is if they're both true. So we got a false, we got a true, we got a false, we got a false. So in this one case where they're both true, we finally get true. Okay? So that is P and not Q, the truth table. I hope you got that. Please come to office hours if any of this is not making enough sense. Okay. Now it's time for something very important. This is going to come up for the rest of our lives now. It's called the conditional operation, or also known as implication. Okay? So there's a symbol for it. It is either the double arrow or the single arrow. And it gives us the if. It gives us the word if. So we want to represent something like, if A is true, then B must also be true. Okay? That's the idea. And let me say must. Let me make it very, very clear. Must also be true. So we need to figure out what the truth table for this is, because we want a mathematical if statement. It's beautiful. So the way we can come up with, we can invent the truth table for implication together. It's going to look like this. P implies Q, or if P then Q is how you pronounce it. Here's my example. So we are going to express something of this nature in logic, and so my example is mowing the lawn, because I did that as a kid. So Dad says he's going to give me $20 if I mow the lawn. Because of inflation, that's probably how much he would have given me today if I did it. Okay, so let's fix some propositional variables. So I'm going to say P is I mow the lawn, and Q is I get $20. So what I'd like to express in logic is P arrow Q, because that's what Dad is telling me, and we want this to be true. He is promising this, so this statement must be true. P implies Q. If P, then Q. if I mow the lawn, then I must get $20. Okay? So P is called the hypothesis, because that's what I want. In a perfect world, I will have mowed the lawn. And the conclusion is what comes from the hypothesis, what is implied by the hypothesis. So that's the I get $20 bit. Okay, so the truth table looks a bit like this, and we need to fill in this bit. Okay, let's do it together. So here's the example reproduced. So we want to determine whether or not it's true here or false here. Okay? What does it mean for P implies Q under these conditions to be true or false? And the answer is, well, was Dad lying to us? That's the way you can look at this. That's the way you can frame this question. Okay? So P and Q, or if P then Q is true, if Dad didn't lie to me, if I mowed the lawn and I got $20, if that happened, that should be true, right? So the question is, when should P arrow Q be false? When should if P then Q be false? That's equivalent to asking, when would we feel cheated by Dad? All right, so let's work on this together. It's going to make sense. So P, again, is I mow the lawn. Q is I get $20. So is it true? Is if P then Q true if I mowed the lawn and I got $20? I hope that question makes sense. It is a bit fuzzy to learn implication for the first time. And it is kind of hard to explain, but with enough practice, you're going to get it. So, did Dad lie to me? He said, if I mow the lawn, I get $20. I mowed the lawn, and I got $20. That seems like a fair deal to me. So, this should be true. And so that's what we're going to put here. It's true in this case. Let me do these other two for a reason. So, if I didn't mow the lawn, but Dad decided to give me $20 anyway, we're in this case. So in that case, anything really goes, and I can't really say much about if P then Q, because I didn't uphold my end of the bargain, but I somehow was $20 richer. So we're going to call this statement to be true in this case, because I failed to uphold my bargain, so I can't say anything about if P then Q. It probably could have been true. So we're going to take the benefit of the doubt from Dad. Okay, same with this case. I did not uphold my requirement. I did not mow the lawn, and I did not get $20. So that says nothing about whether or not Dad cheated me out of money because I didn't do the work. So in this case, we're also going to say true. So if P then Q is true in the case where I didn't uphold the hypothesis. I didn't uphold my end of the bargain. The one case where P implies Q is false is this case here. That's the case where Dad lied to us, okay? And so it's not true that this statement was true, okay? I hope you see how this is all coming together, because this being true means that I mowed the lawn, and this being false means that I did not get the $20. Dad, however, told me that if I mowed the lawn, I would get $20, and I am pissed. That is the case where this is false, okay? It should not be true. This statement should not be true when I did all the work, but I did not get the payoff. When the hypothesis is true, but the conclusion is false. Okay? That is my silly example of this. The book has its own. Hopefully one of them makes sense. Implication is one of the hardest to wrap your minds around, but with enough examples, I hope it will eventually get there. So if anything, for now, just remember that this is the one case where things go wrong, and you can think about it in terms of, were you cheated out, okay? In this case, he didn't do the work, so can't say anything. In this case, he did the work and he got the thing, so yeah, that makes sense. And in this case, he did the work but did not get the payoff, and so it was not true to have said, oh yeah, if you mow the lawn, I'll give you $20. False, Dad. False. Okay, that's implication. We can do many things with implication. We can make up a bunch of different brand new terms based on implication itself. So we can make a term called the converse, of course. The converse of P implies Q, or if P then Q, is if Q then P. So you just swap them. Okay, no, I did not want to do that. I would like to draw, please. So you just swap them. That's called the converse. You swap the hypothesis and the conclusion. So it's like, if Dad gives me $20, then I mow the lawn. So you got to pay me first, Dad, because I didn't trust you before. Got to pay up front. The contrapositive is a fun word of P. If P then Q is not Q implies not P. So you kind of like swap them around and negate it at the same time, which is interesting. Just remember the negation and then also the swapping. So that's the contrapositive. So if Dad doesn't give me $20, then I don't mow the lawn, is how you can think about it. And then finally, the inverse of P arrow Q is not P implies not Q, or if not P, then not Q. So you negate the hypothesis and the conclusion, but you don't swap them. So it's equivalent, or in our example, it's saying, well, if I don't mow the lawn, then Dad doesn't give me $20. And it just so happens that the contrapositive is equivalent to if P then Q. You can use a truth table to figure that out. It has the same true and false values. This one and P implies Q. Interesting, huh? Whereas these two do not. They're not equivalent to saying if P then Q. Swapping them around is not equivalent. But they're equivalent to themselves. I'm going to write the equivalent symbol as like a rainbow. This is equivalent to this, is what I'm trying to say here, which is interesting. And again, you can use truth tables to discover this and prove it. So if P then Q is only equivalent to its contrapositive, and that may become very useful to us later in the class when we try to prove things. It might be easier to prove the contrapositive rather than this, and it will have carried the same weight though. Okay, so yeah, more on this later. There is one more very cool operation that I'd like you to know about right now, and that is called the biconditional. Abbreviated to if because it's pronounced as if and only if. The, oh gosh, I forget the directions, but if I think is swapping the arrow. It's like if the right side, then the left side, and the only if is the normal conditional. So it's both of these at the same time. So yeah, P if and only if Q, we say it's equivalent to P implies Q and Q implies P. Okay, so it's just the and of both of these. That's what the biconditional is. And what it's doing is it's showing you when things are equivalent. It's used when you have things that are equivalent. It's used to define things. Remember my example from the first set of slides? That's what this really meant. I was defining what sorted vectors meant. So equivalence just means that truth values correspond exactly. So they're either both true or they're both false. So this is the truth table for P if and only if Q, and hopefully it all makes sense. So in this case, if we go back to this, if P then Q is true, and if you do it backwards, P implies Q and Q implies P. So if this is true and true, this is true and true, these are both true. Okay, you can follow the example from the other slides. But if one of them is false, like this is true, false, this is therefore false and true, this is the one case where we didn't like the conditional, right? Dad cheated us out, so that's false, and anything with false is false, and symmetrically. And then finally, false, false. That actually ends up being true because we hit the cases of the conditional where we did not uphold our end of the bargain, and so we can't say that it's false, okay? Because we didn't follow our rules. The hypothesis wasn't true to begin with. Okay, so that is the biconditional, and you can see how it's true when both sides have the same value. You see that? So that's what it's trying to assert. It's asserting that things are equivalent. Their values are the same. If they're ever different, then we have false. It's not true that they're both the same, because that's what the biconditional is representing. And this is actually the opposite of exclusive or, so technically, P if and only if Q is equivalent also to not, check this, P, X, or Q. And all of these will become apparent soon. Okay, because we're about to have little baby proofs. And the word for proving that like propositions are equivalent is equivalence. Okay, so we need some more terms because this is a math class and our book is full of them. So let's continue with some more terms here. So we say that a proposition, when you combine it all together, because you can't have just P by itself, like it has two options, true and false. So this definition that I'm about to give you doesn't apply to just a single variable. You have to like combine it. A compound proposition that's combined with some kind of operation. We call it a tautology. That's how you pronounce this word. It's like taut, like you're pulling a string, and ology, the study of it, for no good reason. So it's a tautology if the proposition is always true in every column of the truth table. So for example, P or not P, we can do that real quick. P, oops, oh, I want to write Q. So P can be true or false. Not P is just the opposite. And P or not P, well, one of these is always true in each row, so it's going to be true every time. So this is called a tautology when that happens. And you can come up with tautologies for even larger propositions. It happens. Also, there's the opposite, the dual, if you've heard that term and you're used to it. A proposition is a contradiction if it's always false in every column of the truth table. So just like or and are duals, tautology and contradiction are duals, we say. I'm not going to test you on this term, but if you ever get into fancy math, you might hear that word again. So again, P, not P, and again I want to write Q, and then we have P and not P, and you see where I'm going with this. True, false, false, true. Well, one of these is false, and so we're hitting false in both cases. That's a contradiction. And finally, we have the definition of logically equivalent. Okay, so you got two propositions that are logically equivalent if they have the same truth value in every column. So some statement on one side, some long thing is equivalent if it has the same truth value in every column of the truth table. They're all the same. Okay, that's the idea. So, for example, if you write the truth table for not P or not Q, depending on P and Q, of course, and you write the truth table for not, and then, but first doing P and Q, you will find that they are equivalent. And so their truth values in the final column for each of these, like you write both of them next to each other, they'll both be equal in each case. And another way of writing this, because we know about the biconditional now, is to say, is to use it. We can replace the equivalence sign from math with our new logical equivalence sign. P or not Q, if and only if not P and Q is true. Okay? That's the idea. But it's a special kind of true. And let me prove that to you. It's a special new kind of true. So what does it mean for these to both be the same? So eventually we're gonna, let's just do it all, let's do it right out. P is this, Q is this. We got time. Let's do not P or not Q, and let's do not P and Q first. Dun, dun, dun. And then we'll save this last part for this final thing. And I'll show you what's going down. So true, false, true, false, true, true, false, false. We're experts now. So not P or not Q, darn, they're both false in that case. Not P is false, not Q is true though. This also makes a true, a true. Okay, then we have not P and Q, and you can see how and would be false, true, true, true. Or, I'm sorry, true, false, false, false. But negating that makes false, true, true, true. So they are equivalent, and so if we were to write and use our biconditional, not P or not Q, if and only if not P and Q, writing tiny, sorry, you'll notice that these are all the same. They correspond, and so it's either true, true, or false, false. So the biconditional is always true. Ooh, this is what it means to be equivalent. We have a tautology. Okay? So this equivalence is the same as saying that the biconditional is a tautology. And it decided to use a different font, and that bothers me, so I'm going to change it. Boop. Okay, so that's what it means to be equivalent. You can use the biconditional and get a tautology, which is interesting to think about. That's what it means for both of these to be the same. Okay, so I think that's enough of me rambling. Now it's time for you to practice. All right, so please use a truth table to prove that this statement, P and Q, P and the quantity, not Q or Q, is equivalent to P. So please write one out. It will be very helpful, I promise. All right, assuming you're back, let's do it together. We got our P and our Q. Usually we just go in alphabetical order. We don't have to. We can be crazy. True, false, true, false, true, true, false, false. All right, and then we have, we can do this one. We can do it slowly together to make sure we don't make any mistakes. Let's do the quantity not Q, and then we can use that to build not Q or Q. Yeah. And somehow, in the process of writing this down, I have made lowercases capitals. So let me fix that. P, Q, not Q, not Q or Q, and then P. And then finally, we're going to use all that together to make P and not Q or Q. Okay? So, pardon my horrible straight lines, but let's get started. False, true, false, true. So, to get not Q or Q, we look at both of these columns and see if any of them are true. If so, it's true. So yes, we got a true, we got a true, we got a true. Hey now, we got true. I like that. That's useful. That's actually the reason why this is equivalent. Then we have P, which is, oh, we already had it. I'm confusing my own self. There we go. We don't need that. We just need that one. Silly me. All right. Now let's combine them. Let's AND this with this, but because this is all true, it doesn't really do anything. We just take what we had. It's P again. And that's what we wanted to prove anyway. So true and true is true, true and true is true, true and false is false, true and false and false, false and true is true. Okay, there we go. False and true is false. It's hard to write and talk. I'm sorry. So again, we have this and this. They correspond. They're equivalent. That is the proof. Okay, if you want to get fancy, you can make the biconditional, but that's extra. We don't need that. We don't have time for that. Okay, so yeah, it's fun. It's fun to prove these equivalences, but I'm sure you're tired of it now, and if not now, you'll be tired of it after using truth tables to prove it in your homework. So a bunch of people got together and they decided on a bunch of different rules that they wanted to finally write down for everyone else to use until the end of time, because it's hard writing a truth table. Let's just use some laws so that we don't have to keep writing truth tables. So the first law, the first two laws, I guess, that I want to teach you are very famous. They're named after, I think it was a Dutchman named De Morgan. That's his last name. And his laws tell us how to, what's known as push a negation inward is how we say it. So it's like, I got this negation out here with this quantity, but I don't like that. I like having like the and or be the outermost thing. So I'm going to push the negation inside of these parentheses. That's the idea. So there's an equivalence for that. It's not P, not the quantity P or Q is equivalent, logically equivalent to not P and not Q, having pushed that negation in. Okay, so what happens is you distribute the negation to both elements, to both sides of the OR, and then you also flip the OR to become an AND. Okay, so you bring in the nots, and then you flip the operation from OR to AND. And then it's equivalent to do between, to do the not of an AND, it becomes a bunch of knots of the OR, if that makes sense. And if this is not clear to you, I want you to try it yourself. I think we have already done one of them somewhere. No, I proved it to you here. That's the one. So we proved one of the De Morgan's laws already, and the other one is kind of symmetric. Okay, it's the dual, in a sense. So the idea for these laws, and the reason they're useful, is because it doesn't matter what P and Q are. They can be as big as you want. Like P itself could be, I don't know, X and not R and all of that. And you can keep on going. You can push the negation in as far as you want. So you just keep following the rule. So, for example, I'm going to simplify this very long statement for you by pushing this negation out here. See that there are two parentheses, a parenthesized statement full of parenthesized statements. I'm going to push that negation as far as possible using De Morgan's laws. Okay? So let's break this down into chunks so we can consider it's the not of two things, this statement, this quantity, and this quantity. So I want to push that negation in to both of them. So what's going to happen is we're going to use which De Morgan's law? It'll be this one. We're going to say, okay, I'm going to negate both of those quantities. So not, this becomes not X or not Y. Or, and then I'm going to push it in here, not, got ahead of myself there, not Z and W. You might want to use multiple colors. This gets kind of complicated with all these things, but eventually it will become second nature. So now I have some more statements with a negation outside. We don't like that. That looks weird to us as logicians. We would like to push those negations in. So we're going to use De Morgan's law twice more to get, for the first one, it's going to be not X or, no, sorry, not X and, because it flip-flops from or to and not Y, so you double negate it, that, or not Z, and not W, and that looks a lot better. The only last thing that looks weird are the double negations, and they actually can cancel out and go away, so technically it's just Z. Technically it's just Y, and that's another equivalence that you can prove. But you only have to do it once, and then you can use it until the end of time. Okay, so these are called the laws of logic. These are just a few of them, but they are very, very nice. Okay, they are useful enough to write down so that we don't have to use truth tables for the rest of our lives. Okay, so the list from the book, that is huge. It's on the next slide. Here it is. Look at it. We'll look at it in a second. But the idea is that every time you see one side of an equivalence, you can replace it with the other side, and everything will always still be correct and equivalent. And the reason is because it's true. Okay, these are like somebody's proved these biconditionals, making sure that they're tautologies. That's the idea. Okay, so let's prove, I don't know, what's a juicy one? We already did a De Morgan's law. Let's see here. Ooh, a conditional identity. We're going to like that. So just as the biconditional is the and of both of these, we've shown that. Let me show you that you don't actually need conditional to have a conditional, if that makes any sense at all. P implies Q, or if P then Q, is logically equivalent to just not P or Q. Weird, huh? So let me prove that to you. So this is a very useful law to use because it shows that you only ever need not or an and then you can make whatever you want. So let's do P, let's do Q, And then our end goal is, then we have P implies Q, and then we have not P or Q, so let's do not P first, and then not P or Q. And it's these two columns that we care about right now, this one and this one. All right, let us begin. So true, false, true, false, true, true, false, false. We are experts. Okay, P implies Q, or if P then Q. Well, the only time data is lying to us is this case. The rest are true. Not P, we just flop it. So they were true in these two and false in these two, so we flip-flop them. And then not P or Q, well, here's not P or Q. Is one of them true is what we're asking ourselves. So that one's true. Oh, they're both false there. Oh, they're both true here. Oh, they're both true. Aha! Very, very nice. So we have an equivalence. Okay, and so no matter what P is and Q is, they could be anything because we've proved it for every possible case of what P and Q could be. This stuff is true. Okay? So these are all your fancy laws that you get to use, and yeah, they will be very useful and come in handy. Things like idempotent laws, like you do the same thing to the same thing. Or you do something to the same thing, it's useless. It's as if you had just said P. That's not a problem. Associative laws are useful. They're like the same for like addition, 2 plus 3 plus 5. That's the same as first do the 2 and then the 3 plus 5 together. Okay, so it's either those are together or those are together. You can move the parentheses around. That's the associative law. That works for and or. Commutative laws, also like addition, like you can swap them, or multiplication even. 2 times 3 is the same as 3 times 2. Well, P or Q is the same as Q or P. P and Q is the same as Q and P. Distributive laws, things like multiplication distributing over addition. This is how it works. Like I want to bring the P inside of this. So it becomes P or Q and P or R. And likewise, this becomes P and Q, or P or R, or P and R. Gosh, sorry, this is a lot of symbols. If you or with false, that does nothing. If you and with true, that does nothing. It's an identity. And dually, if you and with false, you always get false, no matter what P was. If you or with true, you always get true, no matter what P was. If you negate twice, you just flip it twice, which is the same as doing nothing. The complement laws means, well, not true is false. That's pretty easy. But P and its negation, one of those has to be false, so it's going to be false. And then likewise, or dually, P or not P, one of those is going to be true, so it has to be true, just because not false is true. All right, so we know the De Morgan's laws. Absorption laws are kind of tricky and interesting. I won't spend, I don't think, any time on them now, but it's fun to think about and useful for simplification, of course, because it'd be a lot easier to write down P than this large thing. And then conditional identities. We've proven this one and this one. Okay, so I've tried to give you some intuition as to what these are and what they mean and why they're useful, but it's only going to make sense when we do it on a problem, right? So that's why this course is structured around problems. So let's do another. All right, so let's use the laws of propositional logic to prove that P and Q implies P is a tautology. Okay, so it's always true, no matter what P and Q are. So that means that instead of writing like a truth table and asking like, okay, what is the thing in every case? It should always be true. That's equivalent to saying that, well, this whole darn thing was true in the first place. It's equivalent to just true. That's the same, okay? So maybe I should write that. That the statement simplifies to just true by itself. Okay, that's a useful concept. Okay, so we want it to just simplify to true. Okay, so we're going to name each rule from this slide that we use, and let's get started. So our original thing is P and Q implies P. Okay, I might have to write smaller. So that's our original thing. That's what we got. And then we're going to simplify that down over here. Okay, so what rules can we use? Well, none of these have conditional operations, but we can get rid of that one. So we can convert a conditional operation into not P or Q. So all of this implies P is the same as, well, if you consider this to be the P, this to be the Q, it's not this or that. So it's not P and Q or P. I hope you see that. Okay, I'm just replacing this with the P, this with the Q, and using our conditional simplification rule. So the name of that is conditional identity. Cond-ident, I will say. Okay, next one. So do we have anything that looks like anything here? Not really. We're kind of waiting on that negation. So the thing that we should probably do here is worry about pushing that inwards, because then we can use our table. That's why we like to push negations inwards. Okay, so let's push that in. I'll use a dotted line. So what's going to happen is we're going to use our De Morgan's law, one of them, and that gives us not P or not Q, because it flops, flip-flops, or P again. I hope you see that. So that is, let's see here, which De Morgan's law? Well, it's one of them. I think we could just say one of them. That's good enough for me. On a test, I'm going to call this De Morgan. And, okay, we're getting there. We're simplifying it down. Now this is like chess. You need to move around these pieces somehow to see what's going to happen. What we would like, and what you're eventually going to be able to see clearly, is that we have P here twice. One as the not, one as the non-not. One is the true version, one is the negated version. So if we put those next to each other and OR them together, do we get, where am I? If we put them together and OR them together, we're going to get true back. There it is. It's the complement identity. It's the complement law. Okay, so what in the world is going to happen there? Well, we need to get these two by themselves together. So we need to like change the parenthesization and get the not P over here. So how are you going to do it is my question to you. Maybe think about it. Take a look at this table. Try to think about it yourself. But what you can do, assuming you've thought about it, is we can swap these first. Okay, we're allowed to do that because OR is commutative. We can use the commutative law to move around that OR. We can put the left side on the right now. So we can say not Q or not P, and then OR P. Okay, that's a commutative law. For OR. And then we can use the associative law to rewrite the parentheses, because we'd really like this, right? We'd like to see this happening right there. So what we can do is use that law, the associative law, to rewrite those parentheses from left to right or right to left. You can go on either side, either way of this equivalence. That's what it means to be an equivalence. So now we have not Q or, we've rewritten the parentheses, not P or P. That is a associative law. So it's like we're relearning algebra for these new operations. And then finally, I want to make this true. We're almost there. Now I have to write smaller. But they're not in the right side. So I want to use this complement law. Eventually you can just say, okay, yeah, it's true, because obviously these are commutative. But we're going to spell it out right now, because we're just learning. So not Q, or I need to flip these in order to use that law. That's written the way it is. P or not P. Okay, so again, I use the commutative law. Or I use commutativity. Let me just for my own sanity, move this up a little bit. Whee! There it goes. All right, so we're home free almost. We need to now make this true. So let's do that. So it becomes not Q or true because of which law? This one right here, it's the complement law. We've got P and the complement of P. So one of those is always going to be true. So we're going to make it true because of the or. And now anything ORed with true is true. Which law is that? Dun, dun, dun. It's the domination law. And we've got it on the right side, so we're cool. True by the domination law. And so we've just proven rigorously that no matter what you do, no matter what P's value is, no matter what Q's truth value is, every row of the table is going to be true anyway. So this simplifies to just truth itself. It's a tautology. Okay? That's the proof. Not too bad, I hope. It's a fun little game. I hope you also agree with me and think it is one. But you're just finding what matches and filling in gaps. Okay, so that's one way. We have gone from, let's see, we've been able to now. We've been able to make our own truth tables and prove stuff about them. We've been able to go from a proposition, a compound proposition even, to a true or false value. So to a truth table for it. We can go the other way as well. So if you give me truth values, I can write you a proposition always. It might not be the simplest one. I can use these rules to simplify it, but I can give you one. So there is a trick, and I want you to learn it now. So if someone gives you a truth table, there is a trick. You can immediately turn it into a proposition. You will be the coolest kid at the party, okay? Oops, and sorry for the silly edit. I had an error in these slides. I swapped and or when I shouldn't have. But the trick is this. The trick is just extract all the true cases. Alternatively, you can extract all the false cases and then negate the entire thing, but let's not deal with that right now. This will make more sense later, probably. But the idea is seeing that this mystery proposition, whatever it is true when P is true and Q is false, or when P is false and Q is true. And I actually just said the answer in words. That's the idea. That's what you want to notice. So if you see, for example, if you notice that it's true when P is false and Q is true, then you should add not P and Q, because that takes care of this line. Let me show you that. So I got my P, got my Q. I've got true, 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 false, false, true, false, false. And then I have not P and not P and Q. So not P is false, false, true, true, and then I'm going to AND them together. And what do you know? The only case where they're both true is that one case I'm trying to extract. Ooh, that's slick. That's beautiful. And likewise, if it's true when P is true and Q is false, what should I add? Take a second to pause the video to make sure you're understanding. I better add. That's right, Dora the Explorer. I should add P and not Q. Okay, so let me make a not Q line. That's going to be false, true, false, true. So this and P, oh man, is that only true in the second row? False, false, false. So if I OR these together, if I OR these two things together, this one and this one, I'm going to get true here, and I'm going to get true here. And oh man, is that the answer? Oh yes, that's lovely. That's beautiful. Okay, so yeah, all you have to do is find the true cases and just say them out loud. P is true and Q is false. So say P and not Q, because that's what it said. That's what it's saying when you use logic this way. It's like, all right, P is true and Q is false. That's why you use negation. Or P is false and Q is true. That's the shorthand. Okay? It took me forever to realize this when I was taking this class as an undergrad. So hopefully that has slightly helped you, because it wasn't spelled out to me. Okay, so yeah. Alternatively, you can do the same thing for false cases because of this fact. You can spell out the false cases with the same idea and then negate the whole darn thing, because then that'll flip false and true. But yeah, this is a nice little statement, and so now we know that whatever this is, it probably has some pretty thing, and it does. I mean, it's really XOR. That's not the point, though. It's equivalent, though, and we just proved that it's equivalent to, gosh, what's something that's visible? Maybe I'll use rainbow. It's equivalent to, no, I'm definitely not using rainbow. It's equivalent to, we'll see if red is contrasty enough. It's equivalent to not P and Q or P and not Q. Okay? So that's my spiel. It will come in handy very soon, if not now. Okay, so now I want you to practice, as usual. So please take a moment to fill in this question mark using our trick. Okay, and so you should be able to read it off right now, and we can verify that it's true. So what are the true cases? This one and this one. So what happens to make this the true case? Well, P is true and Q is true. So P and Q. That gives me the true, false, false, false. It gives me true in this column, or this row, sorry. So that's one of them. And then I OR that with the other true case. So when P is true and Q is false. P and not Q. Okay? And so we can verify that this is going to work. So we've already done this one. So true and true is true. Don't have to worry about this other side. For this one, we have P is true. We can look at this side. And not false, so true and true. We finally get true again. So yes, that's perfect. So that should go here. And then these other ones should be false. And why is that? Well, let's see here. One of them is false in this case, so that's fine. And then again, this is negating the truth, so darn, we get false here as well. And so likewise for this one, and this is the answer. So again, there's probably a more simplified thing, but this is a good one. Okay, so that is going from truth values to propositions. It's a useful thing to know. So we've had propositions now. We have just letters that represent true or false values, but we can do more. We can get fancier. We can include these things called quantifiers, and I want to introduce them before we break for the lecture. Okay, so let's talk about predicates right now. A predicate is just a fancy proposition. Okay, it's a function in proposition land. Okay, so it's a logical statement whose truth value is a function of one or more variables. So I can define this proposition P, and it's like a function involving other propositional variables like x and y, or just members of some set of things like people. So I can say that P of x and y, that's how you pronounce it. You can define it to be this. So I'll use the equals dot, and that's equivalent to equals def is equivalent to, hey, I'm defining this thing. It's a definition. So I'm defining P of x and y to mean that x loves y. Okay, that's a proposition. It can be true or false. Okay, it's still, at the end of the day, once you fill in the variables, it becomes true or false. You get a proposition. That is true and false. True / false. Okay, so I'm going to say that P of x and y is x loves y. So it's true that, and I don't have to say it's true that this, like I can just say this and assert it. That's the same as saying that it's true. We just learned that. So I can say P Lawton, cats. P of Lawton and cats. So that means that I, Lawton, loves cats. I love cats, yes. That is true. That's a true statement, but I do not love the smell of hand sanitizer, which is unfortunate given the pandemic. Okay, so hopefully that makes sense. It's a predicate. It's not true or false yet. You have to apply the function to some propositional variables first. Okay? Yeah. Eventually you're going to get true and false. Let me just write that in here. Okay. Another thing that's very important when you talk about a predicate is the idea of a domain for that predicate. So the domain for this predicate here is just anything, things, or I guess the domain of X is people, and the domain of Y is like whatever, anything that could possibly exist, any idea, anything, any noun. So domain of X is, I guess, people. We can assume that it's people, humans. I guess cats can like things too, but we can choose our domain. Okay, so I'm declaring that the domain of X is people, and the domain of the Y propositional variable in the P predicate is any noun in the world. Okay, so another example makes it a bit easier because we can use numbers. So a domain is just the set of all the possible values for the variables. Okay, so in P of X, if I define it to be X minus 3 is greater than 5, that's a true or false statement. Like you fill in an X, I can tell you whether or not this statement is true. X minus 3 is greater than 5. You know how to graph that, I'm sure. The domain of X could be here, all the integers. Okay, that's totally fine. Like you can plug in P of 42, P of 0, and I think one of those is going to be true. Okay, you can plug in P of pi if you wanted to, or you can restrict the domain. Okay, this is called a domain restriction. Because normally if you just read it yourself, you'd think, oh yeah, it's any number. But no, we can just restrict the domain of P to only be defined or usable when it's X is a multiple of pi. So you can be like, all right, it's pi. You can only use that, P of 2 pi, P of negative 42 pi. Technically, P of 0 is a thing because you can use P of 0 pi, but you get the idea, okay? Every integer multiple of pi, let's say. That's a stronger guarantee. Let's move that over a little bit. Okay, so that's a predicate. That's when you have a variable in your proposition. You have some variables, and it's not a proposition yet even. You have to apply the function to get one. Okay, so I think that's where I want to stop. We're going to add quantifiers now that can like range over these propositional variables, and cool stuff is about to happen. But this is where I want to leave us. So just let the idea of predicates ruminate in your mind, and I will see you in the next lecture. Or actually in your lab. So I'll see you then.